Hello and welcome to 10.8 Taylor and Maclaurin series. We first start by reminding ourselves of Theorem 21, term-by-term differentiation. So if we have a function equal to a power series on some interval, then we could start to express the function in terms of, we could also say the derivative, first derivative of the function, and we would use the power rule. Take n and multiply by cn, drop the power on the n. And second derivative would be take the next iteration of that sequence, so then we multiply n minus 1 times n times cn, and then drop the power on the exponent to make n minus 2. Okay, so we could express term-by-term differentiation on each of the terms in the power series. So that brings us to Taylor series and Maclaurin series. One thing I want to mention before we go further into it is that these two series are basically polynomial approximations of some common series, some common functions that we are introduced to. Okay, so we'll have some examples today we're going to be looking at, and we're going to be generating the Taylor series or the Maclaurin series, depending on the problem. And those will be polynomial approximations of those functions. Okay, so same functions, but in an approximation form, expressed with polynomials. Okay, so we have the Taylor series, all based off of derivatives. So we're going to take the k here. You'll notice the k, which is the index of the series. You'll see it in 3 places. So the k here represents the derivative. So if it's the 0 derivative, first derivative, second derivative, we would evaluate a. Okay, the Taylor series is always centered at x equal to some value a. And then we multiply by x minus a raised to that power. And that derivative, we express it as divided by some k factorial. And so that becomes our Taylor series. Maclaurin series is centered at x equal to 0. So you'll see that the Maclaurin will always look a lot shorter because it doesn't have all these binomials. It'll just have everything will be evaluated at 0. The derivative evaluated at 0, and the original function for the first step evaluated at 0. Okay, you'll still have the x's in it. The x's will just be x squared, x cubed, all the way to x to the n. And then we have a Taylor polynomial of order n, and this is just a polynomial of whatever number of terms, n terms if you will, and that gives us an approximation for the function in terms of what we call a Taylor polynomial. Okay, so it's only a finite. We only have it set for a certain number of terms. Okay, so let's take a look at our first example. So let's find the Taylor series generated by f of x equals 1 over x at a equals 2. Where, if anywhere, does the series converge to 1 over x? So I put the general Taylor series definition here to remind us of what we're going to be doing. So let's take the derivative for our function. So we have the original function. One over x, that's the same as x to negative 1. Let's do the first derivative. So that'll be negative 1 times x, so negative x, drop the power, so negative 2. Let's do second derivative. second derivative of x would be -2 times -1, which is +2. X, drop the power. Okay, and so this will keep going like this. If we did the third derivative, that would give us -3 times 2, so that's -6x. Drop the power on the x, so that's -4. And this will go like this, right? So if we have f to some nth derivative of x, that's going to equal, because of the alternating signs, we would have -1 to the n. And then we have a factorial situation developing, right? Goes from 1 to 2 to 6, so that's going to be n factorial. And then we have x to the negative, and then n plus 1. The negatives will be growing by n plus 1. Okay, so remember, because it's centered at a equals 2, we're going to evaluate all of these, the function, the derivatives at a equal 2. Okay, so that means we have f of 2, which will be 2 to the -1, which is 1/2. F prime of 2 will be -1/2 squared. F double prime of 2, and then this will be over 2 factorial. This will be 2 to the -3. Which is the same as 1/2 to the third. Okay, and this will continue like this. So if we try to come up with our Taylor series, remember the Taylor series would be f of 2 plus first derivative evaluated at 2 times x minus 2 minus, then we have second derivative of 2 over 2 factorial times x minus 2 squared plus, and then we would continue like this, and we would have whatever derivative we are at, nth derivative, evaluated at 2 over n factorial times x minus 2 to the nth power, and we would keep going. Okay, so more specifically for us, this would be 1/2 minus, it would be x minus 2 over 2 factorial times right, well, that would actually be not 2 factorial, but 2 squared, plus x minus 2 squared over 2 cubed minus and then to generalize it would be negative 1 to the n times x minus 2 to the nth power over 2 to the n plus 1. Okay, so that would be the Taylor series. Now, this would also be a geometric series, right? The first term would be 1/2. The ratio, right? The common ratio would be negative x minus 2 over 2. Okay, this would converge absolutely. For x minus 2 to be less than 2. And to come up with the sum, we would have, let's see, sum, we would have 1/2 over 1 minus r which is the same as if we have 1/2 over, and we have double negatives, so 1 plus x minus 2 over 2. Okay, if I multiply top and bottom by 2, let's see that. If I multiply top and bottom by 2, I end up with 1 over 2 plus, the 2 there would cancel, x minus 2. Okay, so the 2 and the negative 2 would cancel, so we would end up with 1 over x. So we end up with the Taylor series generated by the function 1 over x, and it converges to 1 over x for this interval, x minus 2 in absolute value less than 2. And we would say, to be more specific, x minus 2 less than 2 greater than negative 2, add 2. So it converges when x is greater than 0 and less than 4. Okay, so that is our first example. Let's take a look at example 2. It says find the Taylor series and the Taylor polynomials generated by f of x equals e to the x at x equals 0. So when it's x equals 0, this is also the Maclaurin series for e to the x. Okay, so first Maclaurin series, let's just simplify it a little bit. So we're going to figure out what is f of 0, right? And then we're going to do let's do the derivatives first. So we have f of x, and then all the derivatives are going to be the same thing, right? Because e to the x, right? Derivative of e to the x is e to the x. And now if we're evaluating at x equals 0, so that means we have f of 0 equals e to the 0. E to the 0 is 1. F prime of 0 would also be e to the 0, which is 1, so on and so forth. Right? So in general, we know that for the nth derivative of x here would be also e to the x, and the nth derivative when we evaluate at 0 would equal 1 for every number n in the Taylor series. Okay, so let's go to set this up for our series. So we have f of 0 plus f of f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f to the nth derivative over n factorial times x to the nth power Okay, and that means this simplifies too. Well, we get f of 0 is 1, and then f prime of 0 is 1, so 1 times x is x, and then f double prime of 0 is 1, so we have 1 over 2, so it'll be x squared over 2. If we took it another term, it would be f triple prime of 0, so it would be x cubed over 3 factorial, which will be 6, so on and so forth. So it will be x to the n over n factorial. Okay. So the Taylor polynomial of order n at x equals 0 would be this. Okay. You can say p sub n of x equals that, but this will be the polynomial. Alright, let's take a look at example 3. Find the Taylor series and Taylor polynomial generated by f of x equals cosine x at x equals 0. Okay, so again, this would also be a Maclaurin series for cosine of x. Okay, so we need the derivatives. So we know that f of x equals cosine x, f prime of x equals, well, derivative of cosine is negative sine, so negative sine x. If we do second derivative of x, derivative of negative sine would be negative cosine. Third derivative, so So derivative of negative sine would be, negative cosine would be negative of negative, so that would be a positive sine x. Okay, and this is gonna continue, right? Derivative of sine x will be cosine x, and then we repeat the same pattern. So that means every even derivative, right? So second derivative, fourth derivative will be alternating signs between cosine and negative cosine. So we would say f to the 2n, so even number. Okay, and because the alternating sign, we would have negative 1 to the n times cosine x. And then every odd derivative, f to the 2n plus 1, if you will, of x will have a alternating sign with the sign of x. So it'll be negative 1 to the n plus 1 of sine x. Okay, so at x equals 0, the cosines are 1. Alright, so let's remember that. Because this is x equals 0, and the sine equals 0. Okay, so let's set this up for our series. So we're going to be doing f of 0 plus f prime of 0 x plus f double prime of 0 x squared plus f triple prime of 0 over 3 factorial x cubed, so on and so forth. So we would have f nth derivative of 0 over n factorial times x to the n, and this will continue. Okay, so what will this look like? Okay, so f of 0, so if we plug in 0 into cosine, that's 1. Okay, then f prime of 0, so if we plug in into sine, right, we plug in into there, so that would be 0 times x Okay, next we have the second derivative. Second derivative is negative. We have minus. So that would be just a minus x squared over 2 factorial. Okay, so second derivative at 0 gave us 1, but it's a negative cosine, so it's like a negative 1. So we have a negative 1 times x squared, negative x squared. Okay, then we have, it's going to alternate and go, third derivative is sine x, so that's 0. 0 times x cubed. Okay, and then it would continue from there. It would be plus And then we would have x to the 4th over 4 factorial, and so on and so forth. So we would have negative 1 to the n of x. Notice we're going to get all the even powers of x. And then we'll have it over the even power, even number factorial. Okay, so this would be the series. Zero to infinity. Negative 1 to the k power. X to the 2k over 2k factorial. And our polynomial will be equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot 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 plus negative 1 to the n, and then x to the 2n over 2n factorial. Okay, so that would be it. If you have any questions, we'll go through it during class, and I hope to see you guys later. Okay, have a good day, have a good night, see you soon.